Howdy, let's dive into Lesson 7 handout on Expectimax. Question 1, consider the following decision tree. So here we have 3 agents. We have the down triangle that will select the minimum value of its branches. The circle, which will select, will have an equal probability of selecting any branch. So right here it's 50% left, 50% right, but if there's a third branch, every branch would have a 1/3 chance of being selected. The drop triangle is the maximizer node, which will select the highest of either branch, the largest value. So we can actually copy this. What are your assumptions on the different agents? And just answer question A with what we just talked about. Fill in the value of each node. Okay, so now we're going to backtrace this tree and find the value of each node. Let's insert some text. So the first one is a down arrow. So it's going to select the minimum, which is 4. Put that right there. And I'm actually going to add some text boxes to all these guys. Okay, so the first one is 4. The next one is 6. The next one is 3. The next one is 1. And here we have equal probability. So with probability, we're actually going to find the expected value. So there's 50% chance of going to 3. So that's 0.5 times 3. Expand this a little bit. 0.5 times 3 plus 50% chance of going to the right branch to get 1. So 0.5 times 1. And that equals to 2. Hopefully I did that correctly in my head. Now let's try this guy. 50% chance of going left for 4. So plus 50% chance of going right for 6 equals to 3 plus 2, which is 5. And finally we have our maximizer. So our maximizer can select either 5 by going left or 1. Sorry. I believe that's actually 2. 2 by going right. So because it's a maximizer, it selects the highest. And which action would the first agent select? Left branch. Assume you feel the adversary agent will take the left branch 70% of the time and the right branch 30% of the time. Identify the optimal path and branch values for the below Expectimax problem. And that's going to be using this graphic right here. So let's actually move this to the next page. Okay. So our adversary is the circle right here. And it goes left 30% of the time and right 70% of the time. So our values are going to be Let's make this a tad bigger. Our values are going to be 0.7, because we go there 70% of the time, times 5, the value of the left branch, plus 0.3 times -2 equals, make this a little smaller. That equals to, plug into the calculator, 2.9. Awesome. I just want to look pretty. Okay, we'll do, that's really ugly. Okay, we'll do that. We'll do the same right here. Actually, I just thought of a solution to my formatting issues. I'm going to make the background clear. I can make this as big as I want. Okay. So now we have 0.7 times 9 plus 0.3 times 13 equals 10.2. It's a lot higher. So we have 10.2 for this guy. And here we have, this needs to be smaller. -4.7 times -4 plus 0.3 times 10 equals to 0.2. All right, bear with me as I do this for every single expected or probability node. .7 to go left, -7, and then 0.3 to go right to 2. -4.3. Sorry if this is tedious. I promise you that computers do this much faster than I do. All right, last one. .7 chance of going left, -2, and 0.3 chance of going right to 6, 4.4. Yep. Okay. So now we look at the next layer, which are maximizer nodes. These maximizer nodes will select the largest value of its children branches. So between 2.9 and 10, we have, oops, here, let me get one of these text boxes. Between 2.9 and 10, we have 10.2. That is clearly the higher number between the two branches. And here we have 5.2, comparing 0.2 to 5.2. And the bigger between 4.3, -4.3 is 4.3. The bigger one between 1.8 and 1.4, or sorry, just 0.4 is 1.8. Yay, we got another probability node. Okay, so on this layer, we do the same thing. So in this case, again, it's 70% chance of going left, 30% chance going right. So we got 0.7 times 4.3 plus 0.3 times 1.8 equals to equals to, drum roll please, 3.55. Same process over here. Yeah, 0.7 times 10.2 plus 0.3 times 5.2 equals to, what will happen here? 8.7. All right, and we have another maximizer node. Yay, less typing. So the higher between our 8.7 and our 3.55 is 8.7. So that means our final answer that our agent will choose is to go left to achieve the expected value of 8.7. All right, problem 3. Multi-agent minimax for cooperative games. So in this case, we have color-coded nodes. Blue will try to maximize blue. Green will try to maximize green. And red will try to maximize red. So knowing this, we're going to pick the option that gives us the largest blue, because that's our final, that's our ultimate agent at the top that's making the first decision. So let's walk down. Here we have our red node, our red agent or player that will pick the largest, the branch that will result in the largest red, which is the left branch for an 8. So we got 7, 1, 8. And let's see, I will color code it. I'll color code it with highlighter. That's not the highlighter. Green. And red. That's just a little easier to see. Colorblind folks like me need all the help they can get. This agent will pick the left branch because that results in the highest red number. So we have the red branch for 3, 6. That is tedious. 3. There we go. 6. Interesting. I just wanted to highlight. Okay. 6 and 10. Oops. Okay. And here we have another agent, a red agent, that picks the left branch because it has the highest value. Red value of 18. So we're going to move all the values from that leaf up. And finally, we have this guy who's going to pick the left option to maximize the red 7 over -2. All right, and now in a similar vein, we're going to maximize green because our next decision node is a green maximizer. So we're going to pick the left branch because it has a higher green of 10 over -6. Here we're going to select our right branch because 6 is greater than 1. Finally, our blue is going to select the highest blue. So our 3 is greater than 2. So we select the left branch. And ultimately, we go down. We make our first decision is to go left. And we determine the value that each agent would choose in any of these branches in the decision tree. Question 4. Assuming you're determining the preference of a person to play the lottery or not to play the lottery. Odds of winning the lottery are 50%. For the following utility of money, determine if it is better for each agent to win the lottery or just take $500. So this is a little confusing. What it's saying by the following utility of money is that there is a tax. So you can either get $500 flat or you can get $1,000, but this is $1,000 comes with a catch where it goes through one of these functions. So, for example, winning $1,000 for utility function 2 means you actually get $100 because maybe you get taxed or it's in some weird currency. It's just not worth as much as a standard dollar. So let's dive into this. For the first utility function, the utility of every dollar is simply X. So that means that every dollar we make is the same as a standard dollar. So in that case, we can draw out the tree. Let's see, we'll do this with shapes. So we have our first decision node, which is a triangle, actually. And then we can either go left for $500. We'll do a rectangle. Rectangle just means that we get $500, right? If we simply go home, we don't go big, we just take the money and go home. Or we can go right and roll the dice with the probability node. So the probability node is going to have 2 branches, one in which we win and one in which we lose, and it's 50% chance each. So we either win the lottery or lose the lottery. If we win the lottery, then we're very happy and we get $1,000. If we lose, we get $0. And because they're equal chance of either happening, we get $500. Gotta make it a little fatter to fit the number. So our expected value of rolling the dice is $500. This means that there is, in the long run, if you take this lottery many times, there is no difference between just taking the money and rolling the dice, playing the lottery. Because for either one, we can select either branch, and our maximizer will thinks of either branch as equal. So in either case, we expect to win $500, whether we take the money or not. Now let's examine a different scenario. So let's actually write our answer first. Same results. No preference. There's no preference to either play the lottery or take the $500. Personally, I would just take the free money because I would at least walk away with some money to spend on ice cream on the drive home. Now we have utility function 2, which square roots are money that we win from the lottery. So this $1,000 right here that we win from the lottery goes through this utility function and becomes square root of 1,000, which is simply 100. That's not right. Square root of 1,000 is 31.6. So our expected value is 50% of 31.6 plus 50% of 0, which is 15.8. So in this case, our maximizer would clearly choose the left branch. In other words, we would take the money and go home. We would go home. Because the expected value of playing the lottery just went down by a lot when you pass the winnings through this utility function right here. And finally, we have x squared. Our game, when we win the lottery, I guess someone decides to match it by squaring it. So 1,000 becomes, well, 1,000, it becomes 10 with 3 more zeros. So $1,000 becomes $1 million. So in other words, we have a 50% chance of winning $1 million. So the expected value of rolling the dice, playing the lottery, is half of that. And we would take the right, we would play the lottery every time because the winnings are just, potential winnings are just too high to pass up. My nodes are getting wider and wider to fit these numbers. And that wraps up. We would absolutely play the lottery. Unless we really needed $500, like we had a loan shark or something that was going to break our knees on the drive home. Besides that niche circumstance, yes, that is the answer. Thank you for watching, and good luck in AI. Bye.